and then you get what we call a functional. Very similar to a function. I mean, it's not, well, it is inherently, but
Yep.
the interesting thing about this is now this doesn't only depend on a single variable, but it depends on a function that changes with respect to a variable. So maybe we can dive a little deeper into, I don't know,
Certainly.
understanding these higher levels of functions.
Yeah, because ultimately a function is just associating one object with another. That object itself could be a function. That's totally fine. It could be an entire set. It could be literally anything you want it to be. Seriously. It could be a weird set that's kind of ugly and chopped up, which could be a set of real numbers, which you could picture as a weird potato in R3 if you'd like. Or it could be a equally weird set just of functions. If you just picture all sine waves, if you take the origin, take a sine wave, the standard one, just sine x, and then shift it up by a constant and let that constant vary from -1 to 1. So sine x plus c for c and -1 to 1.
Yeah.
You get this continuum of functions. You could pump that entire set through a function if you want. Right? Like you could do whatever you want to do. And functionals are really important in that they give birth to what's called functional analysis, which is something you're going to see in 4th year if you do a pure math degree. But they're really important. They talk about Hilbert spaces, which is everyone here cares about physics, is the kind of language of quantum mechanics a lot of the time, right? We work on L2, which is a set of square integrable functions. Don't worry about what that means. It means that it doesn't get too big, for lack of a better word, and its probability is normalized, which is really important for quantum mechanics. I'm going to assume the viewers, a little bit of probabilistic foundations of quantum. Anyways. Your work point is all the wave functions live in that space. That's a set of functions. And those are the wave functions, given a bit more conditions, but whatever. So this is another instance of where we're not just talking about functions taking things and spitting them out, but we could just talk about a set of functions itself and then do things with them, right? That's like all of what the current quantum model kind of looks like. I'm speaking so heuristically, but I don't think there's the quantum police on me today, I hope.
Like a function space similar to what you're talking about.
Absolutely.
Right?
A function space. The functions. That's what L2 is. The square integrable functions. Defined on blah, 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 blah. Right?
So just understanding.
Yeah. Because functions are a whole lot more than just being able to associate somebody's height with their age or something like that. You know? We might only care about functions with what we can do with them, not even what they input or output, which is kind of the wave function, right? We only really, I don't want to say that. It's a little bit of a stretch. But oftentimes we just like to integrate it to get probabilities. Right?
Yeah, that's
well,
true.
that would be the wave function in particular, but yeah.
Yeah. I mean, those ones at least. I mean, I'm sure maybe in your first year quantum courses, you maybe evaluated it at some points, like capital psi of 0 and stuff like that. But oftentimes you just take its modulus squared and then start doing things. Right?
Yeah, that's right. And Matt, with your wise experience and all that, what do you think are some of the most interesting functions that you've seen?
Isometries. Okay.
Explain.
I'm going to break down what that means. It's two things. Isometry. Metry kind of sounds like metric. It means size. You can measure it. Iso means same. Equivalent. That's why you hear the words, what's it called? Isomorphic, blah, blah, blah. Stuff like this. So isometry is same size. So what that does, we'll do it in a linear algebra sense because everyone here knows basic linear algebra. Think of a vector, a transformation that takes a vector and maps it such that the norm of the vector is equal to the norm it started at. That's an isometry, where it's norm preserving. The norm doesn't change when you do it. So let's think about a way to think about that. Let's take a vector on the unit circle, so a unit vector, norm 1. Picture an isometry. Can it stretch it? No. Can it shrink it? No, because it has to keep it the same length. It just rotates it around. This is a form of an isometry, right? Where these become really useful is when you do this on functions themselves. So you don't just do this on vectors. You might want to associate a form of size to a function itself and then talk about isometries between function spaces so that the function doesn't grow or shrink as it goes through this functional, right? So that's something we do in functional analysis quite a bit. So let's think of a way we can measure a function. You know how to measure a vector. You can associate a length, right?
Yeah, so I'm thinking maybe you can take like an interval and then measure like the length of the actual function, right? And then
I had never heard of that, but that's potentially.
I mean, that's the first thing that I thought of.
Yeah,
when you
because
said,
there's like that
measure a
formula,
function.
right? Like using the integral, how to like find the arc length in an interval. So like that's
Of
actually
a graph, yeah.
similar.
Yeah.